some of these videos played and then they didn't play, so hopefully they work. If not, we'll just look at them from a different place. So basically, this is robot basics, right? So this is where we start picking up some of our terminology that we use in the field of robotics. First thing we have is, hopefully it plays. This shows us, so we have robots, and this is basically what this chapter talks a little bit about, the different classes and what a robot is. Basically, at this college, we don't teach robots, we teach industrial robots. I understand the difference. So there's a lot of things that they consider to be robots that are not considered to be an industrial robot. So to be an industrial robot, we have to have certain things. That makes sense. Right, exactly right. They're industrial robots. It's not where you see Robot Wars. Robot Wars is not an industrial robot. A drone is not an industrial robot because it does not manufacture. Right? You understand? Now we get into different classes of robots. So to be an industrial robot, it's got to be involved in manufacturing. Okay, does that make sense? So these are all industrial robots. We'll learn how to program. We'll get a basic introduction in the program. If you take the operation programming class, you move to the industrial robots. And that's offered in a T2. You're not signed up for it. You're in robotics, and you need to make sure you get into that class. We get an introduction to programming in this class. We're going to program a mobile robot that, if it works, we haven't fired it up in a while. And we're going to program this little gray delay or dark gray robot right here. And we're going to program the Lego robot, which should be the one closest to true programming. So yeah, you're going to get the programming in this class. No, you won't get into the languages until you get into the act. Well, we're going to be introduced to the languages of the robot that we program. Okay. So you have different languages that you have to learn to program the robot. The one for the mobile robot, it's a lot like these guys. It's a text-based language. The Mindstorm programming language is basically like flowchart. It's really neat. It's a really good way to pick up the logic of a program without having to learn a bunch of language. But if you get into the text-based programming language of the actual robot over here, and every one of these programs are different languages. But they're basically the same. You'll learn that when you get into PLC. Way back, the state, Bob James was governor. They gave, before he left, he gave us a ton of money. We went out and bought a bunch of PLC. Absolutely no training on the things at all. They came in, so we figured out how to do it. And that was back Square D. That's a long time ago. They're not in business anymore. But what you find out is that once you program in a language, then it gets you a feel of programming and you understand the logic of it. So all these robots program in a different language, but it would be like me writing programs for the iPhone. Well, the programs for the iPhone will not run on an Android phone, even though they look similar. But I guarantee you, if I learned how to program on my iPhone, I guarantee you I could pick up a language real easy to do the wall. To the Android. So what we're saying, all these robots do the same thing. They make the same moves. Not in this class. We have several PLC classes that if you're in robotics or in AEC manufacturing, I highly recommend that you We actually have 3, huh? PLC, Programmable Logic Control. If you're in manufacturing, we actually have 3 of those. Yeah. We have one where you learn the basics. It'd be kind of like this, but you'll be on an actual PLC. And then we have what we call advanced PLC. They got canceled this time because we only had 2 people registering. And then we're adding a 3rd PLC. I forgot what the title is. It's going to be really interesting. If you're looking to get the Siemens level 2 certification, you probably need to take those 3 classes. So what we start off with here, this is a basic history of industrial robots. Robots that were built specifically to be put into, and hopefully it plays. Of course it don't, but let's go up. I should have left this opened up so I could pull them up here. That's not it. Just the same video. I'll try to get it to play and come back later on, but let's go ahead. What is a robot? But you're getting into an industrial robot. What we're doing here is just good. I mean, it's a good explanation, but what is people consider to be a robot? Well, that could be true.
I think robots are like humans, something to replace a human.
Could be, but we have a term called robot. They call it robots. So you have to be really careful. Every once in a while on the internet, y'all ever hear of a company get what they call denial of service, where they get so many requests for their website that nobody else can get into. It's called denial of service. And then what they'll do is a lot of times you never hear about it because they'll send them an email or something saying, if you give us this much ransom, then we'll give you back your website. But it's not killing the website. What it's doing, it's taking away all the bandwidth that comes into there and nobody else can get in. Well, what they do is people don't understand that is they get a virus or malware installed on their computer, which basically causes your computer to access the website and you never even know about it. And they call those robots. And they call it robots. I mean, so robots And you see these guys on robot boards. Those are not programmed. Those are just RF. Those are just radio controlled cars. That's all they are. But they call them robots, right? You understand? But so those are, they call them robots. Are they robots? Yeah, they're robots. They might not be a high class of robots, but they're robots, right? So robot, that's the problem we have with robots. There's really no what. There's no clear definition of a robot. So it's a very, very interesting topic. But so what y'all is doing is y'all are doing, and it's right. So what you're giving me is the definition of a class of robot, but not what an actual robot is, right? There's no precise definition, but general agreement of a robot. This is general agreement of a robot is what? A programmable machine that indicates the appearance of having intelligence. So, but a robot, when somebody says, you'll hear the term robot used all the time. You'll say, well, that's not a robot. Technically, it might be a robot, but it's going to be a different class of robot, right? We'll look at the different classes in a minute. So good job, guys. To qualify as a robot, a machine has to be able to do what? Get information from the surroundings and do something physical such as move or manipulate objects. So what would a radio control, if I'm out at robot board and I'm running this guy around manually, how is that thing getting information from the environment? To me. Right, you understand? I'm the controller. And to be a robot, you gotta have what we call a controller. You gotta have a controller. So yeah, that would be considered to be a robot, but is it programmable? Well, yeah, because the operator is constantly changing the program, right? It's kind of touchy. So what we have to do is get in, the International Standards Organization, or ISO, defines this as a robot. So now this really gets into getting away from what all these wide categories of robots, right? It says an automatically controlled, so that takes me out, right? You understand that. Reprogrammable multi-purpose manipulator programming in 3 or more axes. So this is what ISO defines a robot. So when they throw that out, that eliminates, that robot board is what? It's out, because right at that first word says, the second word says what? Automatically controlled. And anything that's autonomous means it does it with little or no human intervention, right? Everybody okay here? By the way, these PowerPoints are up on Blackboard. I hope they are. Now, this is the guy that we're looking at is the Robot Industries Association. Huh? The Robot Industries Association. So this guy gets into industry, so this is where we get into defining what an industrial robot is. So to be an industrial robot is a reprogrammable, multifunctional manipulator designed to move material parts, tools, or specialized devices through a variable programmable motion for the performance of a variety of tasks. So reprogrammable, what does that mean? It means the end user can change what it does, right? You understand? Everybody okay? What's a manipulator? Move stuff around. Gotta be able to move stuff around, right? To understand there. Of course, a variety of parts and devices. Now, RIA has went into this programmable in case the robot is a machine whose actions are controlled by a stored program that can be changed by the end user. Everybody understand that? The manipulator can perform multifunctionally can perform more than one function. To be a robot, it needs to have several of these. It's not natural, so it's artificial, right? It's man-made. Can sense the environment, can manipulate things in the environment, has some degree of intelligence or ability to make decisions based on the environment. Now, this is the touchy thing right here, is that robots run programs, computers run programs. So what, if somebody says, what does a computer do? There's only one answer. What does a computer do? It runs programs. Period. Everything that you see these computers do was written by a person that we call a programmer. From the time you turn it on, it runs programs. So when we say, some degree of intelligence, where does it get its intelligence from? Programs. But they appear to be, it's amazing to me. Some of these people, and I wrote about the program, some of the things that these people are doing with programs. Even some of our games appear to be artificial intelligence. They really, really. You got to understand, somebody figured out how to do that kind of stuff, which is amazing too. Is programmable, can move with one or more axes of rotation or translation. So what they're saying, or translation, is it don't have to be a rotary axis. It can be linear axis. We have two types of axes that will run robots. On the manufacturing line, you can see both those types of robots. One of them has linear axis and one of them has rotary axis. All these have rotary axis. Can make dexterous or very fine coordinated movements and appears to have intent and agency, which that's a good term.
When it says it can sense the environment, do you mean like when the robot the other day sensed that the block was not
there or not there? Right. See, of course, that depends on something. We got a whole lecture on sensors. So sensors. So even these robots over there they have the ability. But we're not using these robots for years. But when we say sense the environment, that would be it sense its exact position in space. So all these robots are sensing their environment, even though, and I go over there and I open the door, well, if it's an automatic mode, the robot stops. But even that robot there, and every one of them has we can hook up tons of sensors to the robot. And we could also hook up a programmable logic controller that feeds into the controller. So we can add a lot of features to the robot that we can add on, right? You understand? So all these robots are what we call companions. We can add more to it. But just having the ability to sense where it's at is sensing its environment, right? You understand? So that would be part of it, sensing the environment, sensing where things are at, sensing when things are not there, sensing color, sensing all kind of things. We have sensors. We have all types of sensors out there that's available to us. So sensors have been around so long, there's very few things that we can sense that we can't do that with what we call it. So can it sense its environment? Yes, so it has to have that ability. One of the most primary things on all this robot is just knowing where it's at all the time, or the computer knows where it's at. So this is what RIA has actually came up with 4 robot classes. So Robot Wars would be Class A robots, because these are what? Manually controlled. A lot of your drones are manually. So I've got a little drone, quadrocopter, but it's totally manually controlled. We went to a thing down in Mobile, played around with some drones, and those things are neat. Because, you'd be flying, you could program a predefined path, how the thing would fly, and if it got out and got away from the radio, from your transmitter, it'd turn around and come back. You could tell it to come home. would remember where you was at. So you didn't have to fly it home. You just say, come home. You know, so you'd be flying that thing all over the place and you say, okay, come home. And you turn around and fly back. Auto land, so you didn't have to land it. So, it was tricky landing on drone too. It would come down and you set it down really nice and pretty. Automatically handles device with predetermined cycles. Most people refer to these as automated machines. And automation has been around for years. You need some of
No, find out your area in mind. That's Mr. Raymond. He can take the class.
So, okay? These cycles are usually set by mechanics. So automated manufacturing has been around for years. These devices are not necessarily programmable, but they run a set program, right? But basically it's set up by limits, what we call hard stop. Programmable servo control. Servo is a term that you need to learn. Servo means these are devices that provide feedback. So right now, if I go over there and turn off a light, what type of feedback do you know that you have that the light is turned off? Your side. But if I had a switch over here on this wall that turned off the lights next door, how would I know the lights were off? You wouldn't. Yeah, you wouldn't. We call those non-servo, right? Don't understand that. So a servo system is a system where we tell something what to do, and then it gives us feedback that says it's done. So open loop would be like the accelerator on your car. How many of y'all are supposed to be traveling 70 miles an hour when you get down and you're doing like 90? Right? Because you're not looking at your phone. But we have a cruise control. You use that cruise control, you got that, and you have feedback now. You have a sensor that indicates the speed of the car. And if the car is going too slow, what does it do? Speeds it up. If it's going too fast, it automatically slows it down. That's what we call a servo system. Also called a closed loop. So those terms are used interchangeably. So closed loop and servo means these are systems that provide feedback indicating that they do what you tell it to do. So when we get into automated systems, it's not a class D, and we're going to deal with sensors, right? Now, class D robot is where we add, it's a class C, but what do we add the capabilities to do? Sense its environment, right? Everything in class C, plus they add the ability to sense its environment. So all these robots right here are class D robots. So this basically takes in almost everything that we consider to be a robot, and it's software robots that come in with a computer, and you don't even know about it. The International Federation of Robotics. This gives us some statistics, and this is robots. These industrial robots. Shows that the record number of industrial robots is being installed. Sales increased by 29% in 2014. In 2014, there was 1.5 million machines out there. By 2018, there's supposed to be an additional 1.3 million. So being in robot manufacturers is a good business to be in. Robots enable manufacturers to reduce direct and overhead costs, making a dramatic difference to their competitiveness. And this is what we were talking about. Thank goodness for industrial robots, because we would be making foreign cars in the United States. So they're kind of not foreign cars anymore, right? They're designed overseas, but they're manufactured where? Here. because of industrial robots. And why? Because now it's cheaper to do what? Make them here than to make them there and ship them here. But thank goodness, if it wasn't for industrial robots, we would be still getting cars from Germany. We still are. Mercedes would still be manufacturing them where? In Germany and shipping them over. But now they manufacture them here. Because now it's cheaper to make them here than it is what to do what? Make them there and ship them over. So robots do different things, and one of the main features of a robot, and hopefully my video plays, I think I can find this one, is to do what? Think. And I don't think we ran the Festo line over there. The robot on the Amatro line it serves the function of what we call machine. The robot on the Festo line is an assembly robot. So what would be the difference? Well, a machine tending robot just moves parts between machines. An assembly robot does what? Puts parts together. So let's see if this works. So these are manufacturing terms. So we have mass production, batch production, hard automation. And then there'll be some other terms that the book talks about. So mass production. What is mass production? Yeah. Then we have batch production. So what would Mercedes do? Well, you got to understand we can do both. Yeah, you got all these different options. Well, these options, they don't put all those options in every car. They don't paint every car red. They don't paint every car green. So their color, their paint shop would probably be batch, right? You understand? Their whole process would be mass, right? You understand? If they do 15 cars that has a special option in there, which they do, they'll try to do those in batch. Right? Okay. What's neat about the paint line? We'll look at the Kia manufacturing line. Their batch production is really neat. So they can paint any car, any color, any. So they don't have to run 15 reds. They don't want to have 5 greens. They can run a red. The next one could be a green. The next one could be a white. The way their paint line is set up, but that would still be considered to be batch production. Hard automation, these are machines designed and built to run single products. These are not automation. These are not reprogrammable. There's a lot of those. Automated manufacturing has been around for years. You ever watch How It's Made? And that thing comes out and spins that little spring around. That's how long has that video been going? Well, that would be an unprogrammable machine, right? But it's automated. Nobody's out there doing it. So automated manufacturing has been around for a long time. This is called hard automation. So the sequence in hard automation is done by the machine itself, right? It's designed to do it certain way. So these are our manufacturing categories. Project manufacturing, job shop manufacturing, batch, repetitive, and continuous. And every bit of this is in chapter 1. So project manufacturing, these are complex, non-repetitive activities. These produce large-scale, one-of-a-kind devices or units made to order parts. And of course, examples is, we see this all the time, buildings. All right, you understand? Road projects, bridges, these are what we call project manufacturing. So these are examples of project manufacturing. Building roads, building bridges. So what do? These usually are designed unique, they're usually customer specific. They go out there, they spend months and months and months get it done in one day. Hopefully they move on to the next problem. If they're a good manufacturer and they're very, very flexible, and they could do a lot of different projects. Are we okay? This is what we call job shop machine. I did some part-time work for a company called Beaches Machinery, which is out in Fairfield. And they had a bunch of machines up. And every machine did a certain function. And what they would do is they would get an order, or they would have to do something, and the route it went through the machine shop would depend on what that part needed. So this example right here, they're bringing in all different types of devices, and then they take different paths. So the yellow one, see, it comes in what? Yeah, it goes to machine 1. I'm sorry, this round one. Goes to machine 1, then goes what? To machine 5, and then goes to the machine 6, and it's through. The green one comes in and does what? Goes to machine 2, goes to machine 3, goes to machine 5, and it's what? It's through. So all the machines are basically, you can't say they're dedicated, because most machine shops either are going to be CNC machines or they're going to be manually operated machines. More and more manually operated machines are still out there, but you don't see many of them anymore. About most of the machine shops are going to what we call numerical control, CNC, computer numerical control. But the path it takes to that would depend on the job, right? You understand? Yeah, I did some work for that company. Really an interesting job. So the guy said he was paying me too much. And this is the same one. This is one that's in your textbook. This is just a little better one that makes it, to me, a little easier to understand because they do colors. Are you okay there? Well, okay. I like some of the hairdos and stuff. Robot tending. So here we have a robot, and the robot is not actually, all it's doing is manipulating, right? It's just doing what? Moving stuff between machines. And on the Amatrol line over there that we showed y'all last class, that's what that robot does. It doesn't do any assembly. All it does is just move that block between what? Different machines that's already there. Don't look like this is complete. I think I can do this. Sorry, thought I had it running. Robot is loading a leg, right? Loading a leg. So you can see all it's doing. This is pretty neat. This line. This robot has a linear action. So the tool on that thing is real neat. So it goes down and picks up one, spins it around, and puts down the other. So machine king, everybody okay? Pretty neat. That's been around for years. In fact, the first industrial robot that was installed in the General Motors plant did what? Machine king. That's what it did. Just moved the parts between that. Did you hear some of the terms they said? They said programs, it's program. So everything you see that thing was doing was written by what? By program. By the way, in robotics, we don't call it writing programs, we call it teaching. It was taught by a program. Flexible manufacturing. This is a lot like job shop, but the only difference is all the machines here are totally programmable in what we call flexible manufacturing. And if a machine, we still have machines that do tasks, but they are all programmable. Does that make sense? So flexible manufacturing means I could probably run 1 part or 2 parts or 10 parts, depending on what the customer needs. See, robot right here, later on we'll learn about classes. So what's the difference between job shop and this guy? So if they use machinery, how did they get the parts between the machines? Huh? But how did the parts move? Who determined the routes? How did the parts get between them? Who loaded the parts in and out of it? Huh? People. Right? You understand that. Job shop. So each of the machines, they had overhead cranes all over the place. How would they literally move the parts between the machines? Right. And how many people did you have at every machine? You had somebody at every machine, right? You had an operator at every machine. This guy, how did it move between the machines? See the robot moving around? A rectangular robot moving the same spot around. How many people did you see at the machine? None. All of the programs, right? Somebody programmed. So flexible manufacturing is basically, you can't say it's totally automated. Luckily, you still have to have people around. I think if you look at iRobot, they have robots building robots, right? But, odds are that's never going to happen in our lifetime either. I'm not saying it's going to. Definitely not in my lifetime, and not in your lifetime either. Which is pretty neat. So flexible machining is a lot like machine shop, but what's nice about flexible manufacturing is it's automated, right? But once it gets on that carriage, once somebody puts the part on that first carriage, it's moved to every machine, and every machine does what it's programmed to do until it comes out of the finished product. Are we okay? About job shop, machine tending. I don't know what's in here, nothing. Flexible manufacturing, job shop. Let's see what I don't see one for this video right here. So transfer line. So a transfer line usually uses hard automation, but usually it uses some automated device to move it between the sections of the line. Y'all understand that? What's it? Transfer. Right here, transfer. Oh, the presses are actually hard animation, right? And the beam here is hard automation too. Well, we see a lot of the transfer now done with robots. So the robots would be considered machine tending, but it would be part of the transfer line. Does that make sense? So what's happening is the presses themselves would be hard automation. You know what a press is, right? So it has a die down in there and presses metal in to form the shape of it. And they don't try to do it all in one most of the time because it puts so much stress on the metal to start off with a chunk of metal and end up with a big product. So they bend it a lot, a little bit at a time. So each die bends it into the shape that they want a little more. And then you got to get it between the dies. So we got one. I wish I could find that. I got to find that. Did I tell you about the Chinese plant? So they got a big die, and they got 4 big stations on the die, and the guys are inside the press. And what they do is they have little grippers. They go over there and grab it, and they move it to the next place, and then everybody leans down like this. And the big press comes down and goes boom, and then they all set up and they move it. So that would be manually. That would be a transfer line, right? You understand? That would be actually people do that. I got to find that one. Instead of talking about it, I got to find it. But so the transfer between machines could be automated, or it could be with the machines themselves, or what we call hard automation. And the only way you change those things out is to change the die. So surely, these cars that press these doors and everything. So we'll show y'all the Kia plant in a minute. It's called Start Finish. That's a really, really good series, by the way. And the Kia plant. Mercedes plant is not a manufacturing plant. The Mercedes plant is an assembly plant. You understand that? So they don't manufacture the car, they assemble the car. So who manufactures these parts? Well, we call them tier 1 suppliers. These are the guys that's built up all around Vance, gas pump, Lexington Gate Road. They're all right around the plant there. They manufacture the parts, and they supply them to the stadiums, and they put the parts together. The Kia plant is a manufacturing plant. But what they do is they bring in rolls of steel. 23 and a half hours later, the car comes out of the oven as a finished product. And they got one of the biggest stamps available. We'll see that thing in a minute, which is really neat.
Back here.
The Kia plant is, I can't keep up with the ones that are around here. I think, yeah, I think here we have Hyundai, we have Mercedes, we have,
Are all Mercedes, those both.
I don't know about the Hyundai plant down in Montgomery. Nancy took a tour of that. We need to ask about that. But I know for a fact the Mercedes plant here is an assembly plant. So you talk about how many robots, and we talked to a guy, and I saw somewhere that gave the number. But we had a guy that was working on a project for Mercedes and with robots down there. He said there's over 3,000 robots, industrial robots in the Mercedes plant. Then you got to visualize how many's got gas dump and how many's got collection gauge and how many's got roads and all these other tier ones. And then you can add those to the robots that are inside that would actually take to produce that car. And for every robot, you can't say every robot is replacing a person. Because what we would see when they assemble the car, so a car could be assembled by one person. Everybody understand that? So, if you look at the assembly plant where they actually put all the sheet metal and everything on, where they put the sheet metal on all the stages, they go through stations, and each station has 6 robots. It's a transfer line, so what do? They'll put a piece of sheet metal on there, and all 6 robots will come in, and they're all welding at the same time. And then when they weld that part on, what do they do? Then it moves down to the next station. They add more sheet metal, and another set of robots do the same thing. So you can't say that every robot replaces a person, because, like I said, a car could be built literally by one person, but how long would it take? It would take 23 and a half hours for one person to build it. We're talking about start to finish, right? Not only putting on all the sheet metal, but also, of course, the Kia plant, they don't build the engines there, so the engines are built all the way. So there's even manufacturing plants a lot of times don't build everything from scratch. They do build the whole body of the car. So they don't make the tires at the Kia plant. Continuous manufacturing, very large volumes of very low variety, specialized equipment, performs a narrow range of functions, very efficient, does not usually use robots. How many of these things are out there? There's still. If I'm making the same product that I've made for years, and it's still a popular product, I'm not going to come in and put automation in there to make it programmable, because my programs would never change. Right? Understand? So we've seen videos of a marble making, automated marble making facility, and how long is the marble from that? Now, of course, if I was to build a new plant, then we wouldn't probably do this. But my old plant is just doing exactly what it says. And the industry has a tendency to not change things that are working. So that's why if you went to work for a plant like U.S. Steel, U.S. Steel used to be out there, you would run into stuff that's extremely old, and you would run into stuff that's extremely new, right? So when I worked as an electronic repairman out there, that was probably one of the most interesting jobs I ever got into, because it was so flexible on what we worked on. Everybody okay here? So this uses a lot of hard automation. These guys use a lot of hard automation. They run the same thing all the time. Not hard automation. This says the welding head like one that's on Banner. Of course, the size and shape varies what the robot is. This would be an example of transfer. These guys are coming in on a piece of metal. The robot comes in and packs metal. We call this spot welding. If you ever took off the bolt steel, rubber girl steel around your board, you'd see all that crap sit on there and pop. That's a big old press. This robot would be doing what? Cheese eating, right? Manufacturing. I don't know if this, how many people, how many people, this will not be correct. Okay, we'll go ahead and take a 10-minute break. If you missed, I call roll at the start of class, and I need to do that. When we get people called here or looking for people for a job, we can't give out grades or anything like that. Y'all understand that? What's the two most often questions I get asked? Are they on time?
Do they show up?
And do they? Well, that's the same. How well do they work with us? That's the two most often questions I get asked about coming forward. So you got to understand. I don't know what you will do. I don't know how you will do if you got a job. All I know is how you do in my classes. So, when they call me, that you use me as a job reference, which is really good. And I'm not representing the college, right? You use me personally as a job reference. And I say, yeah, you had straight A's. You showed up, right? So, y'all understand what I'm saying? And if we still have problems, so we got a class that's got 18 people enrolled in it, and I come in here, there's 5 people when the class starts. That's not really good. So I've already called roll. So if you came in late, you need to come up here and let me get your name on roll. One thing. That could affect your financial aid, especially this week when we have to submit attendance this Friday. That's when they're going to say, okay, who's on financial aid and who's coming. Right? Understand that. You need to make sure you get on roll. So we're taking a break. It's about 7 after, so 10:17 we'll start the class back up. If you wasn't here when I call roll, and by the way, I stopped calling roll after a second. I still do roll, but right now I'm calling roll because I don't know y'all, right? You understand? But as we move through here and I learn your names, I'll do roll, but I still do roll at the start of class. Everybody understand that? All right. So if you wasn't here, you gotta come get on the row, right? Nope. Yeah, let's go here. Oops. Okay, what's your name? What's your last name? Okay.
What is that? When do you have to?
No, I call row then too. I don't know. I have to go look at my row. What's your last name? Okay, good. Well,
The reason I play today, I wear night shoes,
okay.
so I get off. They tell me, we'll let you off before 8:30,
Yeah, there.
I'm rushing to get over here.
Well, I appreciate you getting here. But thank you. But make sure when you come in late, you let me know, because I call roll at the first class. So this is when most of the accidents occur in robotics. That's why we're programming, right? Or we call it teaching. Because most of the time, what happens is you can't teach a robot a program, a position, unless you're close enough to make sure it's in that. I understand. So probably 99% of the time when you program the robot, you are in the work cell with the robot. Work cell. What would y'all think that? Cell. We heard that term several times. Work cell.
Does it look like the plastic roll around it, or not?
Well, it's everything that the robot can get to. Sometimes we can find the site. We'll talk about later on different types of spaces. So all our robots, except for the Big Fanic, well, that's not even true. The Big Fanic, we operated within what we call a restricted space. So basically, the work cell is everything that the robot can get to. It would be considered inside the work cell. Robot Industries Association has redefined that and called it a workspace. So you might hear your people call it workspace. Just about everybody in the robotics industry calls it a workspace. So normally when we program the robot or teach the robot, we are in the work cell with the robot. And this is where a lot of the accidents occur. Because people have a tendency to let their mind drift around, right, understand, and not pay attention to what they're doing. While you're testing the program, now robots, we have when we jog the robot while we're teaching it. Jogging is when we move electric motors, right, to get something in position. So jogging is a manual term. So when we use the term jogging, that's when we manually move a motor. Of course, these robots have all types of motors on them to get something into a position. That makes sense. So what they do is no matter this is OSHA and this is IRA, so all these robots do this, is that when you jog the robot, the speed is limited to 250 millimeters per second, or about 9.5 inches per second. And it's been proven that the robot hits you, you have time to get out of the way of it. That's what I'm saying. Fast, but it's not too fast. I think that's right. I might do my conversion wrong. I know it's 250 millimeters per second, which would be 2.5 centimeters. No, 250, 25 centimeters. Now, when we take, but some of these robots support what we call a high-speed teach. So the KUKA supports a high-speed teach. The Big ADD supports a high-speed teach. Now, that doesn't mean when you're jogging the robot, it's when you're testing the program out. So we have the ability to test the program without switching it into automatic mode. If the robot supports a high-speed teach, then it can run the speed of production. If you're in the work cell on these robots and you run it on high-speed teach, you'll get in trouble. But you still have the teach pendant in your hand. You still have the dead man switch in your hand. And you still are having to press buttons on the teach pendant to run the program. Robots that don't support a high-speed teach, they are limited to 250 millimeters per second. Maximum, huh? I've got that.
That's still fast.
So y'all understand that? So if you got a high-speed teach and you're in that work cell and you're running a program to test it out, you got to really, really be careful on what you're doing. Because you can be in the work cell and not teach much, right? Of course, inspecting, getting out there, screwing around, and then of course repairing. Small robots, it's not really that problem. Big robots, a lot of times they climb up on those things. Not as bad on the robot, right? Sometimes, just keep the fans up, the ladders in there and stuff like that. So a lot of that happens just when you get on the robot over the next something. By far the most wildest one is when you're doing teaching them. Robot safety. First of all, OSHA has adopted the Robot Industry Association 15.06. Most people call it 1506 standard. And the last time that I know it was updated, I need to check, it was 2004. And OSHA has adopted that as part of their safety for robotics. This specifies a lot of stuff. One thing it specifies is what we call safeguard. What would you think of? Safeguard. Around the robot, safeguard. Now, normally the safeguards usually don't come into play when you're teaching the robot or jogging the robot. Everybody understand that? Safeguarding comes into play when you switch the robot to the automatic. And you switch that circuit to automatic, and you run that program, it is automatic, right? What would it do? It will repeat that program. They'll repeat it once. Well, run it once. You notice there's very few robot programs that run one time. They're usually what we refer to as looping programs, which just means what? Over 90% of programs that you see on these computers right now. These guys are running programs, even though they appear to be stationary, it's running a program. So what's it do? So it says so it talks about safeguarding, it talks about training, it talks about different companies often implementing additional safety standards. So the 1506 is just like OSHA. OSHA is law, right? But it's only law for companies that do interstate business. So if I've got a local place that manufactures something and I do it myself, then you're not basically under OSHA. If I've got an electrical license in the state of Alabama and I go out and wire a house, I am not under OSHA. Everybody understand that? Now we have two safety standards. We have. Anybody heard of the National Electrical Code? I haven't heard of the National Electrical Code. What is National Electrical Code? Well, a lot of people think that NEC is the law. NEC is not law until it's adopted by the authority having jurisdiction. So that means, and then so the National Electrical Code covers the safe installation of electrical equipment. That's what it does. So like gauging wires, how do you pack the wires up, how do you do this, how do you do that, how much wire you can put in the box, how much you can load in a conduit, right? You understand? That's National Electrical Code. The National Electrical Code is put out by the National Fire and Protection Association, NAFPA. And then they revise the National Electrical Code every 3 years. And then it's up to the authority having jurisdiction where you're working at, whether it's law or whether it's not law. So Jefferson County adopts the NEC. Okay, the last one I know was 2020. This is 2017, so that means they've got one past that. 2015. That's when my last, what I understood, Jefferson hadn't adopted it yet. You can understand this book is about this big. Before I adopt it, I want to make sure that everything in there applies to what we do. Then they can add additional laws that are regional. So not only do they get all this stuff that's done by the National Fire Protection Association, they can also add additional stuff to their law, right?
What did you say, NFPA was what?
National Fire Protection Association. Standard is NAFTA 70.
about everybody was called it. The electrician will cover the thing. Or most electricians, you find out that it's common sense. You know, that there's some code. That there's some things that are not in the National Electrical Code that they're accepted by the authority having jurisdiction. I think the city of Birmingham, their inspection don't allow you to put more than 15 unit plugs on a run. That's not in the National Electrical Code. Does say you're never supposed to see 80% of your regular budget. Yeah, but that's 1 amp per plug, or 15 amp plug. So you could literally get 15. They say this is a lot of people don't understand that. They say if you got a 15 amp breaker on your house, you can load that thing down to 15 amps. According to National Electrical Code, you can never load it over 12.5 amps. They think that the circuit breakers in there to protect the load. Circuit breakers are not designed to protect the load. They're designed to protect the industrial devices. You know, the conductors that provide the load are running off those walls in your house. You're situating the load is what they do in the house. Do what? It's on fire. So if you've got a circuit breaker that's popping, it's a 15 amp breaker, don't go out and buy a 20 amp breaker to put it in there.
Even though that sounds like something my father-in-law would have done. They did come out with since OSHA has a ton of rules. OSHA is, what is OSHA? Occupational health and safety, right? So this is law, but it only is law if your company does law. Interstate. So what they realized in the electrical field was that you needed some type of law, not law, some type of document that could be adopted that would cover your safety. So 70 standard, the EEC does not cover your safety. The safety installation of electrical equipment. Now, of course, probably 90% of the time, if you install stuff safely, it's going to keep you safe. So this is there for so what they did is they came out with 70E. Everybody ever 70E? If you go to work for a company in the state of Alabama, you're going to hear about 70E. 70E is rules that protect the employee. And is that law? No. It's only if it's what? It's only if it's adopted. And OSHA has adopted the 70, the NAFTA 70, and you can adopt that every year. But they have not adopted the 70E. But if you follow the 70E, you meet the requirements of the OSHA 1910, which is their big book. Has all their safety in there for just about every type of thing you can talk about. Basically, none of them. It was OSHA, but OSHA was a lot different back then. They didn't play around with employers that much. It's just like EPA. So what we had to do at U.S. Steel is we had to have a camera mounted on every smokestack that was in Fairfield and Indian. So when did they do all their polluting? At night. So the cameras couldn't see. That's true. So they monitor those furnaces really, really well during the day, right? Make sure they wouldn't put anything white smoke. And at night they was out there to make money. They went out. Of course, that's changed a lot now. So the 1506 is the main safety rules for robotics. And you can look this up, of course. So
odds are, but it's OSHA, right? And remember, if you're working at a company that does not do interstate, then they're not under what? OSHA. But if they are under OSHA, then OSHA has, OSHA has adopted the 1506 standard for industrial robot safety, which identifies and we'll talk about this later, identifies what safety requirements, where each stop buttons have to be located. So if you look at every one of these buttons, every one of these robots, the big red mushroom button, we call that a new stop button. You'll see there's one on the teach pendant and there's one on the control. So that's the minimum requirements that IRA says that where these stop buttons have to be. But how many stop buttons can you have? You got a lot. But then it's up to the company, right? You understand? Well, they require these stop buttons. But IRA only says you got to have at least one. Two. That's one on the controller, which is the computer that runs the robot, and one on the teach pendant, which is that little computer that you hold in your hand to teach the robot. To do what we call online control. So this has been adopted by OSHA. Companies also implement additional safety standards, and this is what we're talking about. So if I go out there and I put 5, we had one line, number 4 gallon line flying at US Steel. That sucker must have had 30 stop buttons. And you'd be out there working and somebody wanted to take a break, and what would they do? They hit one of these stop buttons. The whole line would shut down. Everybody, while they're trying to figure it out, they'd give everybody a break. And it took them a while to go around and find all these stop buttons. So we set up a big panel board that showed all these stop buttons that when they were pressed, each one was kicked out. So. Work cell design. So you understand what the work cell is. So what is the work cell? It's the space that the robot is operating within, right? Understand that. So that's the cell. So the design of the work cell depends on several things. Of course, the task the robot will perform, the location of the robot, startup and programming procedures, normal mode operation, possible malfunction and corrective actions, electrical, hydraulic, pneumatic, and mechanical stored energy hazards. This gets a lot of people hurt too. Normally, robots use at least two sources of power. They probably use electrical power, and they probably use fluid power. The problem we have with electrical actuators, like motors, is these guys don't like to be stalled. They don't like to be forced to stop while we have energy applied. So most electric motors, if you stall them, they will burn up. They're not protected. Fluid power don't care. So if I want to leave pressure on something 24 hours a day, I'm not going to do it with electric motors. I'm going to do it with water, fluid. So the problem is we'll have people that will go out and work on a robot, and they kill the electrical power to the robot, but they don't kill the fluid power to the robot. Or fluid power, if I kill electrical power, the electrical power is gone, right? If I kill fluid power, most of the time pressure is still in the system. So one thing they forget to do is they might go out and kill the compressor. Anybody got a compressor at their house? You go out there and turn your compressor on. What happens to the power? What happens to the compressed air? If it's a good system, when the robot came in for the Amatrol line, it's got its own little compressor on there. And we plugged it up and turned it on, and the robot ran fine. And you say, man, that's a quiet compressor because we're using compressor on all the time. And that dang robot must have ran for a week before the compressor gets on all the time. So I mean, that system in there was so sealed up that when they checked it out at the plant last time, it still had pressure in that tank. And that must, there's no telling how long it's been since that robot came. I mean, it was boxed up. get these fluid systems, hydraulics, normally if you don't have what we call an accumulator is a system that maintains pressure even if your pump is tight. You usually have a big old tank and it's got a big old weight on the top of it, or a big spring, something like that, and the system's running, the fluid pushes it up, and then it turns off, and that big old weight up there does what? Maintains pressure in the system. This is very, very popular, because if I've got a robot out there holding something up in the air, power fails, and it loses its pressure, then what could happen? It could literally drop the load, right? So that's a very popular movement. Pneumatics hold pressure. How long does it take to bleed that pressure off? Well, it depends on how sealed up your pneumatic system is. So what you need to do is make sure that you not only do you disable the power sources, you also bleed off the power sources that have what? That maintain their pressure even when their pumps or their compressor motors are not running. So just about every one of these systems have that ability, right? Shut down and lockout tagout. So lockout tagout is a method. So in the industry, basically every power source is supposed to have a method of locking out the power. So we actually put a lock on there. These have to be key locks, by the way. They can't be combination locks. How many keys are there? Usually there's one. That belongs to the owner of the lock. Well, you got to identify who the owner of the lock is, right? Who's the only one that's got the key. So what we do is, anytime we put a lock, we put a tag on that lock. And what some of the information that's got to be on the tag is who the lock belongs to. That makes sense. We can tag without locking, but we can't lock without tagging. That makes sense. So sometimes we put a tag just to convey information. Sometimes when we put a lock, and we got to put a tag on it that says this is who this belongs to. And who can remove the lock? Unless there's very extenuating circumstances. So another person can remove the lock, but they got to get permission from the person that put it on there, or they've got to exhaust everything. It's got to be a person of authority, by the way. Can remove the lock. They got to get permission from them, or they got to exhaust all means to get in touch with the person. That would be awful if I've got a plant, somebody's lock's out there, and they're going home and get killed, and I can't take the lock off. Right one thing. But yeah, other people can take that lock off, but it's got to be really extenuating circumstances to do that. And they cut them off that way. When we was out at U.S. Steel, when I was there, our locks had 2 keys. And then you kept one, and then they kept one, and the administrator off. But what I understand, they changed that. It's only 1 key. And you're the one that's got it. So if they can't get in touch with you, what are they going to do? They cut the lock off. They got to really justify that. Lockout, tag out. And you're supposed to lock out and tag out not only the electrical energy, you're supposed to lock out and tag out every power source. Everybody understand that? If you've got power sources that store energy, then you need to do what? Leave that energy off. That gets a lot of people hurt too. Safeguarding, fixed barriers. So we have what we call fixed barriers over there. These are fixed barriers. What do those fixed barriers do?
Like a wall?
A wall or a fence. They use a lot of fences, but unless it's like a welding robot or something like that. Because most of the time we still like to keep our eyes on them. Robots usually, even though they're closed loop systems, they're servo systems, you still use a lot of open loop stuff in there. So anytime, usually cruise control is considered to be standard equipment, but for years it was like what we call optional. So when you got a car, it didn't have cruise control on it. So you had to pay extra for it, right? And that's still, so every option you get on a car, they don't give it to you free, right? You have to do what? That's not true. Sometimes they have selling features where they say, for a limited time, we're going to give you this free. But normally, for options on automobile, you pay extra. But they got to add something to it. So closed loop is great, but closed loop adds a lot of cost to the manufacturing process. So if we was to go over there and look at some of these manufacturers, even this line over here, we'd see the robot, if there's not a piston over there on the Festo line, the robot will swing around there and go down and grip up, pick up, swing around, even if there's not even there. Because to add that feature, it would add more cost to the line, right? You understand? So this would be one of those situations where you would have to have a person out there kind of keeping an eye on that, keep those pistons loaded into those magazines, right?
So what we're, I don't know how we got into it. How did we get into it? But fixed, interlocking barriers. What's interlocking barriers?
Interlocking barriers is usually a barrier that we can move, right? You understand? But there's a method in there that interlocks it with control. So right now these are fixed right here. This back wall is fixed, right? You understand? But somewhere on that cell we got at least one bolt. So that wouldn't be considered fixed, but it's interlocked. So that means if the robot's in automatic mode, if I go over there and open up that door, what's the robot going to do? It's going to stop. Everybody understand that?
Presence sensing devices. So we have, sometimes we can't put the robot in a fixed barrier. We can't put it in an interlock barrier. So we have all these types of sensing devices that indicate when somebody starts approaching that robot. We have what we call a light curve. So if I've got to constantly move stuff in and out of the robot cell, we're not going to have fixed barriers around that, right? But we don't want it to get into the path of the robot, and the robot is operating in automatic mode. So right now, if I was to flip that big panic robot into the automatic mode, it has no idea if anybody's around that thing. If you walk into that robot's path, it will flat wipe you out. Because there's no sensor on it. So that's why we don't run that robot in automatic mode. It supports the full PT. It supports what we call full PT. So what that means is I can run it in the manual mode and see exactly how fast it would run if I put that robot in production. So you was watching the robot run at full speed. What I was doing it in walk with the P-spin. So I was the safeguard. E-stop button, we talked about that, right? You understand? Usually, we have two things that initiate braking. Most robots maintain their position with the actuator. Some robots maintain their position with brakes. If you hit the E-stop, then the robot is on brake. We don't like using E-stop. Because robots, when they brake, especially that big fan, we'll go over there and look at the brake pack on it. It's got all that inertia built up in it, right? Anything that's in motion wants to do what? Yeah, I want to continue. So you'll see that big old robot. If I hit the E-stop, you see the boom. You check around a lot. It's got a lot of mass, a lot of inertia, which could cause it to do what? Could cause it to lose load. Yeah, because it's a loose flow. You know, because if the load's in motion and the robot comes to a hard stop like that, it could actually lose the load and you could get people hurt.
You mean the load, meaning the whatever?
Whatever is moving around. It's just like any time. You should E-stop is that E stands for what? Emergency. So everything has a way to stop it without hitting E-stop. So if we look at the FESO, if we look at the Amtro line, you'll see it's got a red button called stop. If we look at these robots, they got like a hold button, or they got some other type of button that you can hit. And if you hit, the robot's going to stop, and it's going to do an accelerated stop, right? So it's going to accelerate, and it's going to decelerate and stop. And that way, if it's carrying something at the time, it's not going to do what? It's not going to drop. It's not going to cause it again. So E-stop, that E is exactly what it says. It says emergency stop. So if you can't think about it, so this is one thing that you do on that teach pin, that is you, when you get into operation and programming, that you learn where things are on that thing, right? It's kind of like when you get into a new car. You know they all have the same thing. It's just that they might be located here. So my wife's van, her air conditioning control looks just like, and it's about the same place as the control for my radio. So I'm in there trying to turn up the volume on the radio when I'm changing the air. Her shifter on her car is up on the dash, and my shifter is down in the floor. Her windshield wipers is on this side, and my windshield wipers are left. Now they all do the same thing, right? It's just that. So when you go out and buy a new car, what's one of the things you start doing right there? Learning where all these controls are, right? So that's what you need to do. You get into operation program. Learn where these controls are at. We had our mobile robot out there one time. A guy was standing there. I was controlling the manual, and I took off, and he thought the robot was going crazy. He reached down there and jerked the wires out of the bag. So you need to find that button on the robot that's the stop button, right? Not the what? Not the E-stop button. But if something happens, that's the only thing you can hit, and that's the one you need to watch. You need to hit.
There's no stop button on that. See,
Yeah, it is. It's called hold.
I saw that on.
Yeah. Well, no. It's on the controller, the thing that you're holding in your hand.
If you're over there, it's like you did.
It's an automatic. It's in auto mode if you're not, because if you're in manual mode, and I'm not paying attention, that's why we don't let y'all program that. We program these robots that all have safeguard stuff, right? But remember, when you're in there programming, you're trying to pick up a block. You're trying to move it halfway down the block, make sure it's working. How are you going to tell when you get down halfway on the block? Odds are you're going to have to be with it. You're going to have to be in there with it, right? Or if you want to try to put it 5 millimeters above the surface, then by George, you're going to have to get in there and measure that. Because you can't let the robot in. So braking, E-stops are going to cause braking. They're going to cause braking. So we try to avoid that. If you let go of the dead-man switch while the robot's in motion, it will do what? It will brake. It will brake. It won't decelerate, it will brake. So we don't want to do it that way. So we don't want to stop it while it's in automatic mode by releasing that dead-man switch. We can avoid that. That's why they call it a dead-man switch, right? So it's very similar to an E-stop button. It still needs power on a lot of stuff. The E-stop button doesn't necessarily remove power. A lot of people say if you hit an E-stop, it removes power. Is that true? No, it's an E-stop. It's not an E-turn it off. It's an E-stop. Y'all understand that? So just because you hit the E-stop doesn't mean everything's going to turn off. The robot will brake. If I want to turn off power, then I find the power disconnect and I turn it off and block it out, right? Y'all understand that? So the only way you remove power from a device, so y'all watch out for that on multiple.
E-stop removes power, what you gonna say? No, odds are it don't. Just being aware. This is where most people get hurt. This is what causes most traffic accidents, right? You know what I'm saying? Is people are just not aware. They're busy what? Texting or changing the station on the radio or doing something like that, and they're not aware. They're traveling along at 70 miles an hour, 80 miles an hour, right? You're covering 5 or 6 miles. You're covering a lot of area in a second, right? You understand that? So you say, well, I just looked at it in a second, right? Being aware. In warning systems, most of your plants, we don't have those, but most of your plants have flashing lights when these robots are in. They'll have a big amber light up there spinning around and showing you that these things should just be aware. And watch out for these warning devices you got with these plants. This is fences. And notice this is a fence. And so if you went down to Mercedes, their robots, their assembly robots are using inside fences because they're depending on things to be at exactly the right place at the right time. If it's not, then the robot is usually going to crash or it's going to spit something out. And then what do you have to do? You have to be able to see that, right? You have to be able to go inside the work cell and take care of that. But if you're in automatic mode, as soon as you open up a work, it's set up right. As soon as you open up a door to go inside that, or as soon as you go to a light curtain, or as soon as you step on a pressure mat, then what should happen? The robot should stop. Now the robot stops, and you have to reinitiate the program, right? You don't have to start it over. You just have to tell it to start from where it's at. So these safety devices, if you step on a mat, the robot can stop, right? They usually stop. When you step on these safeguard devices, the robot does not brake. It does what? Stop. It decelerates. It doesn't decelerate. Stop. Then you step off the mat. Then how do you start the program going? Well, you got to go over there to that peak pin or remote terminal. We'll talk about that later on. And you'll have to hit a button. Maybe clear a fault, right? You understand? Hit a button. And the program should take up right where you left off. And there's a lot of rules about safety fences too. They got to be high enough. They got to be low enough so you can't crawl under them. They got to be high enough so it's hard for people to go up, climb over them, or step over. This would be an example of what we call a light curtain. Pressure mats or safety mats. A light curtain. So what they do is they just have a big old roll of lights shooting beams across there. And they got a big old roll of light sensors on the other side. You can't see them right underneath. It's like when you see movies and they show you the laser beam. You see laser beam? No. It's like seeing the flashlight, the beam of the flashlight before it hits the wall. So the only way we can see light is if it does what? If it hits something. So if they had smoke out there, see the beam. You see that a lot where they want you to see the beam, they'll actually put smoke in there. So what's nice about this, it allows the cell to be open. So that means I can have a card or something bringing something into the cell, right? You understand? What light curtains usually are set up in different spaces. So when a cart comes in, they can disable a certain section of the curtain and leave the rest of it in place. Pressure mats, these are just mats when you step on them, they sense you're in there. This is the kind of stuff we would use if the work cell had to be open, which means we had to come in different ways inside the work cell. Pressure mats, step on them, some of your old road controls still have that. This is the first automatic door opener you used to have long ago. They had rails beside the doors to make sure you stepped on the mat, right? Remember that? You step on the mat and the doors would open for you. Now they use motion detectors primarily. Camera systems. ABB's got a camera system which is really neat, where the robot runs at different speeds depending how close you are. So you
get into a certain space, the robot will slow down. And the closer you get to it, the robot slows down until you get inside a specific space or operational space, and then it stops. Those are pretty neat systems. So how we do this is several different ways. Control device. This is an example of what we refer to as a teach pin. Teach pin. We have different methods. We have two primary methods we can teach a robot. We can do what we call online programming. Online programming is when you program at the robot. So if I program or teach the program at the teach pin, we would call that online programming. So if you take the operation and programming class, that is an online programming class. Probably 85 to 90% of robot programs are done online. We have another class that we teach, robot manufacturing and computer simulation, which is the way the other probably 10% of robot programs are written. What we do is, in that class, that we basically design a 3D model of the workstation. And then we put an animated robot in there. That is the robot. The animated robot is made by the robot manufacturer. You place that in the work cell, you build all your models and everything on that. I'll show you an example of that. You can program the robot with an animation. And then what you can do is you can take that program that you did on an animation, and you can go over there and upload it into the real robot and run the program. Now, we call that offline programming. The advantage of offline programming is that the robot is not out of production while they're programming the robot. So down there at Mercedes, they got 3,000 robots and they're trying to go to next year's model. How long would you think it would take? Programming a robot takes a long time. You'll find that out if you take the operation and programming. So it would probably take over a year to write the program to run next year's model. So they would be not making cars for over a year. So do they do online programming? No. They have a 3D model of the entire production line. And they write they're programming next year's models right now. It really surprised me. We had the guy come in on my Kuka, they work at Mercedes for Kuka. And he says, I gotta get back to the plant, we're writing our program for next year's model. Then, so Mercedes is down like 3 weeks. They're not down. They go out and upload the programs and then they check everything out. From what I understand, they scrap the first 300 cars. But scrap is sold, right? So they scrap the parts. They don't scrap the parts. They probably sell the parts. That's when they're getting all the bugs out. The programs are primarily written offline. So if you go to work for Gaston, odds are it's not going to be offline programming because that's a stamp shop, right? And their robots are primarily transfer robots going between the stamps. If you go to work for Mercedes or a company that cannot be out while they're doing next year's version, you'll be doing what's called offline programming. So we'll do offline programming for the Mindstorm robot and the Hero robot. That's exactly right. So online is where you write the program at the robot, right? Directly into the controller. Offline programming is when you do the program on a computer that's not the computer that runs the robot, and then you do what? Then you upload it. Offline programming is really neat. So if I've got an accurate 3D model of my work cell, we can literally go over to this robot. We can take a program on that robot. We can download it into a compact flash card. We can bring it over here, upload it into the simulation. The robot over there is still running like crazy. We can make modifications over here, and we can take it over there and upload it. And the robot was basically out of production maybe 5 minutes. So if I've got a problem, it's okay to do it. I just want to change a little bit on my program. I'm trying to get I'm trying to decrease the cycle time. So most robots run cycles, right? You understand that? The amount of time that cycle takes depends on how fast you can push stuff out. So one of the biggest things we're doing with robots is constantly trying to reduce the cycle time. How long does it take to go through that cycle? And of course, so they'll try things out. And what's nice about it is that if I'm trying it out over here, and my robot's still running the old program, it's no problem. If I go over there and I upload it, it don't work quite right, it's okay, right? And I can just go back to the old program and come over and play around with it. So offline programming is really, really neat. But it all depends on the accuracy of the model.
After we do our next break, which we should be doing right now.
So PLC is offline.
Yes,
Go on.
that's exactly right. PLCs are programmed offline. But PLCs, you program over here, right? You understand? That's not true. Some PLCs allow you to modify a program online. But you have to be connected to the PLC.
Here, that you say online program, you walk over, you actually
Pick up that chip, pick up the chip, and you program. No, you hit buttons.
You object.
We have different ways robots are programmed. We'll talk about continuous path and point to point. All these robots right here are what we call point to point robots. So what we do on these robots is we program points, which is probably 90% of the programming out there. And depending on the type of move, it would determine how it moves between those points. So what I would do is I would take the robot, I would move to where I wanted to go. And I would say, okay, remember this point. But when I say remember that point, I said, how do I want to move from the previous point that it was at? That makes sense. We call those point-to-point robots, and these are probably 90% of robots out there. Continuous path robots is you can literally go out there and you grab that robot and you put it in what we call a floating situation. You go out there and grab that robot and you move it through the path you want it to remember. And it records those. Those are probably maybe 10% of the robots out there. It takes a lot of money. It takes a very complicated controller to be able to do that. So we'll show y'all that too. We've got some videos of a continuous path robot. The little Lego robot that we have can be either point to point or continuous path. We'll take the little car and we'll roll it around on the floor, and then we'll come back and put it back over here and tell it to run the program, and it'll do that. But it takes a lot of memory to do that. So if I go over there and I write my program using this teach pendant, then that is what we call online programming. And you're right, PLCs are predominantly offline programs. So what's nice about a PLC is I can write a PLC program and not even hook it up to a PLC. But a lot of times you can't really do a lot of programming, but most of the time you can do minor modifications on a PLC while it's online. So if you wanted to change the time of the timer, a lot of times you can do that. And you can do the same with a PLC. So I can take a program that's in the PLC and I can download it into my computer with an application. You can't do that on everything. So to do offline programming for that robot, I've got to have an application on my computer that allows me to do that, right? So we have two here. We have RSLogix, which that's the application program that we use to program the Allen Bradley PLC. And then we have what we call the Step 7 software that we use to program the signal. You can't just go over there and just write a program unless you have the application to write the program. It's just like if I wrote programs for the Android, I usually have an application I run on my computer that allows me to write programs in a high-level language, right, that I can understand. And then we do what we call compiling over to binary language. Good questions. Any more? So that's basically it for this chapter. Well, we're not through. It's time to take another break. So we'll come back. I'm going to show y'all the Kia manufacturing plant. Show y'all the amount of automation in that thing. It's unbelievable. And what we want to do when we see that is we want to see basically how long does it take before the first human touches the car. We're not talking about you out here looking at panels and stuff like that. We're talking about when it actually goes into manufacturing, the first unit actually takes that part. Kia plant is a manufacturing plant, which is when it's on like that. You know? Well, also, what are the video? I'll show you all the history of robots. I'll have to pull that out. Industrial robots. We talked about the history of robots last class, right? And we'll look at the history of industrial robots. Okay, guys, I'll take a 10-minute break.
As well, he just has